Hello and welcome. We're all interacting with artificial intelligence pretty much every single day. And a lot of the time, we don't even give it a second thought. But what happens when that AI makes a really critical decision, one that affects our lives? How do we ever know if we can actually trust it? Today, we're going to explore the two main paths we can take to finally understand the why behind an AI's decision. Just imagine this for a moment. You've applied for a really important loan, and an algorithm rejects you. Or maybe a medical system recommends a specific treatment. You'd want to know why, right? Of course you would. And look, this isn't just some abstract idea. It's right at the heart of building AI that we can actually rely on. Because without understanding, there can be no real trust. So how do we solve this problem of the AI black box? Well, it turns out there are two quite distinct ways of thinking about it. The first is to build transparency in from the very beginning. We call this explainability by design. The second is to take an incredibly powerful but complex model and use special tools to look inside after it's been trained. That one's called post-hoc explainability. Let's start by walking down that first path. Right. This first approach is all about creating models that are, by their very nature, simple and easy to understand. The best way to think about it is like building a house with walls made of glass. You don't need any special gadgets to see what's going on inside, you just look. And that's why we call them glass box models.
Now, a perfect example of a glass box is the decision tree. And the beautiful thing about it is just how simple it is. It works exactly like a flowchart you might draw out yourself, making decisions based on a series of straightforward if-then questions.
Let's stick with that loan application example. The model's logic is crystal clear. First, it asks, is the person's income over £50,000? If it's a yes, they're approved. Simple. If it's a no, it just moves on to the next question. Is their credit score over 700? If yes, they're approved. And if that's also a no, then they're rejected. You can literally trace the exact path the AI took to get to its answer. There's nothing hidden. Okay, so that's for a yes or no answer. But what if you want to predict an actual number, like say the price of a house? For that, we can turn to another classic glass box model, linear regression.
So the model might come up with a formula that looks something like this. What it's telling us is that it's learned that for every single square meter you add to a house's size, the price goes up by £5,000. And for every extra bedroom, you can add £20,000. The impact of each feature is perfectly clear. You can quantify it. It's direct, it's simple, it's transparent by its very design. And it's not just those two, There's a whole family of these glass box models. You've got logistic regression, which is great for telling you the probability of something happening. There's k-nearest neighbors, or KNN, which basically makes decisions by looking at the most similar examples it's seen before, kind of like a majority vote. And then you have things like generalized additive models, or GAMs, which are clever because they can handle more complex relationships while still letting you see exactly how they work. The key thing they all share is that their inner workings are wide open for us to inspect. And that, right there, is the whole philosophy of Path 1. The explanation isn't some extra thing you bolt on at the end. The explanation is the model. But, and this is a big but, this simplicity often comes with a trade-off. What happens when the problems we're trying to solve are so complex that we need a lot more predictive power?
And that leads us right into our second path. You see, sometimes to get the absolute best performance on really tough problems like understanding language or identifying objects in an image, we need to use models like deep neural networks. These are true black boxes. Their immense complexity is what makes them so powerful, but it's also what makes them so hard to understand. So the question becomes, how do we peer inside them? Well, we develop tools to help us open that box after it's been built. So post-hoc explainability is really the art of applying a special interpretation layer on top of a model that's already been trained. We're not changing the complex model at all, we're just using some very clever techniques to ask it questions and figure out how it's thinking. Okay, one of the most intuitive ways to do this is a technique called permutation importance. Here's how it works. Let's say we've got a model that's predicting if someone will default on a loan. We want to know how important their income is. So we take the whole income column in our dataset and we just randomly shuffle it up. By doing that, we break any real connection between income and whether someone defaulted. Then we run the data through the model again and see how much worse its predictions get. If the accuracy takes a nosedive, well, then we know for sure that income was a really crucial factor. But that gives us a big picture view. What if we need to know why one specific person had their loan application denied? For that, we have a couple of incredibly powerful tools called SHAP and LIME.
Their entire job is to zoom in on a single individual prediction and show us exactly how each piece of information contributed to that one specific result.
And here's what that might actually look like using SHAP. It's almost like a balance sheet for the final decision. For this rejected loan, it shows that the applicant's low income had a strong negative push. Their high debt also pushed things towards rejection. But, on the other hand, their good credit history gave a little push in the positive direction. You can see how all the forces add up to the final answer. Now, this kind of approach isn't just for numbers on a spreadsheet. It gets really cool when you look at something like image recognition. Think about a complex, deep learning model like a convolutional neural network, or CNN. These things learn to see by building up layers of understanding. First, they see simple edges, then shapes, then more complex features like eyes and ears. So when a CNN says that's a cat, how do we know it's not just looking at the rug the cat is sitting on? Well, a technique called class activation mapping, or CAM, can generate a heat map over the original photo. It literally highlights the exact pixels the AI focused on the most to make its decision. In this case, lighting up the cat's face and its whiskers. It gives us a visual explanation. But maybe the most powerful and, let's be honest, the most human way to explain something is with a counterfactual. Instead of just giving you a no with a list of reasons, this system tells you what would have needed to be different. Something like, you would have been approved for the loan if your income had been just £10,000 higher. Now that's not just an explanation, is it? It's genuinely actionable advice. It gives people a clear path forward.
All right, so we've walked down two pretty different paths now, but they're both heading towards the same goal, transparency. Let's just put them side by side for a moment to really nail down the differences.
Right, so the biggest difference is when you apply the explanation. With by design, it's a choice you make right at the very start when you're building the model, and it's perfect for simpler, more transparent systems. Post-hoc, on the other hand, comes in after the model has been trained, and it's designed specifically for those complex, black box systems where you absolutely need the highest performance. One has transparency built right in. The other adds it on later. And if you remember one thing from all this, I hope it's this analogy. Explainability by design is like building a glass house. The structure is transparent from the very outset. Post-hoc explainability is like being given a torch when you have to go into a dark, pre-existing room so you can shine it around and figure out what's inside. So where does that leave us then? We have these two powerful and really quite different strategies for looking inside the mind of a machine.
Look, neither one of these paths is better than the other. They're just different tools for different jobs. The ultimate goal for both is to build our confidence in these systems, either by choosing to build them simply and clearly from the start, or by inventing clever ways to make the complex ones understandable after the fact.
Because at the end of the day, that's the whole point, isn't it? Whether we build a glass box or learn how to unlock a black one, we're moving towards the future where AI isn't just powerful, but it's also accountable, reliable, and something we can fundamentally trust.
This ability to ask why, well, that changes the whole game. It's the absolute foundation for responsible innovation. So the final question isn't really for the developers, it's for all of us. As these tools for understanding become more common, which decisions in our own lives are we ready to entrust to an AI that we can finally understand?